Welcome back to the channel. And today's session we are going to discuss the shift of chatbot to AI agents. It is the next revolution of artificial intelligence, the shift that changes everything. So far, most of us have interested with the AI through chatbots like ChatGPT. The process is simple. You look a question, you ask a question. The AI gives you an answer. Conversation is over. That's incredibly useful. But there is one important limitation. It's completely reactive. It only responds when you ask something. Now imagine different scenario. Instead of asking the AI a question, you assign it a mission. For example, analyze my top three competitors, compare their products, pricing and marketing strategy, create a professional report, and email it to my team. Now, instead of waiting for your next instruction, after every step, the AI figure out the entire workflow on its own. It gathers information, organizes the data, writes the report, and finally send it to the right people. That is the fundamental difference between a chatbot and an AI agent. So, a chatbot answers, an AI agent completes the task. What makes an AI agent different? An agent is designed to work towards a goal with minimal human intervention. To do that, it combines several important capabilities. It can understand what's happening around it. It can reason through complex problems. It can make decisions. It can use different tools when needed. And it can improve its approach as new information becomes available. So the keyword here is autonomy. In simple terms, autonomy means the ability to make decisions and carry out action without someone guiding every single step. That's what makes an AI agent such a major leap forward. So, 5 qualities of a true AI agent. Not every AI system deserves to be called an agent. There are 5 characteristics that separate real AI agents from ordinary chatbots. Number 1, perception. First comes perception. Before an AI agent can make decision, it needs to gather information. Depending on its permission, it might read a document, browse website, receives API data, analyze images. The better it understands its environment, the better decision it can make. Second one is reasoning. Rather than jumping to conclusion, the agent breaks a problem into smaller pieces of evaluates different ways to solve it. So this reasoning process allows it to choose smarter action instead of random ones. And third one is planning. Unlike chatbots that only reacts to one prompt at a time, an AI agent plan ahead. It creates a sequence of steps that require to reach the final objective. Even better, if new information appears halfway through the task, it can revise its plan and continue moving towards the goal. Next, fourth step is taking action. Planning alone isn't enough. Agents can actually perform actions. For example, they may search the web, execute the code, read or create files, send emails, connect with external software using APIs. In other words, they don't just think, they do. The final characteristic is adaptation. As the agent receives feedback, it updates its understanding. If something fails, it tries a different approach. If one strategy works better, it remembers that for future decisions. This continuous adjustment makes AI agent much more flexible than traditional chatbots. So, a typical chatbot demonstrates only a small portion of these abilities. A true AI agent combines all 5. That's why it can automate much more complicated work. Now, how AI agent actually works? Behind every AI agent is a repeating decision-making cycle. No matter how advanced the system becomes, the basic process stays remarkably similar. Think of it as an endless loop. Step 1 is observe. Everything starts with the gathering information. The input could be a user's request, result from previous action, a system notification, even an error message. The agent first collects everything it needs before making any decision. In step 2, think. Next comes reasoning. The language model evaluates the available information and asks itself questions like, what is the objective? What have I already completed? What information I am missing? What is the smallest next action? This internal reasoning helps guide every decision. And in step 3, that is act, after deciding what to do, the agent takes action. It may search the internet, execute a program, read a document, query a database, use another external tool. Or if the objective has already been completed, it simply returns the final answer. So in step 4, learn from the result. Every action produces feedback. The agent examines the outcome. If the information is useful, it updates its understanding. If the result isn't enough, it thinks again and performs another action. This loop repeats until one of 3 things happen. The task is successfully completed, the maximum number of allowed steps is reached, an unexpected problem stops the process. Different researchers give this cycle different names. Someone call it observe, think, act. Other call it perceive, reason, execute. So the names vary, but concept remains exactly the same. So understanding this loop is one of the most important foundation of AI agent. Next is the React framework. One popular approach used by many AI agents is called React, which stands for reasoning plus acting. The idea is straightforward. Before performing any action, the agent first reasons about what it should do. Instead of blindly calling a tool, it explains its next step internally. This provides several advantages, like it reduces unnecessary actions, it creates a logical chain of decisions, and it becomes much easier to understand why the agent behaves a certain way if something goes wrong. Imagine asking, what is the weather in Tokyo? And should I carry an umbrella or not? The agent's reasoning might look like this. First, it recognizes that it needs current weather information. Then it calls a weather service. The service reports 18 degrees Celsius, light rain, high humidity. So using that information, the agent concludes, since rain is expected, carrying an umbrella is a good idea. This is simple, sounds logical, step by step. That's the essence of React approach. Next is tools. The real superpower behind AI agent is large language models are incredibly capable, but by themselves they are limited. They only know what was included in the training. They cannot automatically access live information. They can't read your private files. They can't send emails on your behalf, and they can't directly interact with the software. So think of them as a brilliant expert sitting inside a room with no internet connection. To unlock their full potential, they need tools. So a tool is simply an external capability the AI can use whenever it is necessary. So instead of relying only on memory, the agent can interact with the outside world. Modern AI models have been trained to decide which tool should be used, when it should be used, what information should be passed into that tool. This capability is commonly called function calling or tool use. It's one of the biggest reasons AI agents have become so powerful. So some common categories of AI tools. Information tools. These help agents collect fresh information. Example includes search engines. We know that search engines like Google, etc., Yahoo, etc., knowledge bases, news services, weather APIs. Next is the computation tools. Whenever calculation becomes too complex, agents can use tools like Python, calculators, database queries, SQL systems. File management tools. These allow agents to work with documents. They can read PDFs, analyze spreadsheet, process Word documents, generate new reports. Next is communication tool. Agents can also interact with people through services such as email, team chat platforms, calendar application. AI to AI tools. Interestingly, one AI can even use another AI. Sounds interesting? For example, the agent might generate images, translate languages, convert text into speech, summarize audio. So different AI systems can work together to complete a larger workflow. Next is the parallel tool execution. Modern AI agents don't always work on a task at a time. Suppose you ask for weather updates in Tokyo and London. Instead of checking one city and waiting for checking the other, the agent can request both forecasts simultaneously. Once both responses arrive, it combines the information into a single answer. Running multiple tools in parallel saves time and makes the entire system much more efficient. Now the question arises, why tools description matters? There is only one final detail about that surprisingly important, and many beginners overlook it. An AI agent doesn't magically know what every tool is designed to do. Obviously, instead it reads description that developers provide for each tool and use that information to decide whether it's the right choice or not. Think of it as like hiring an employee for a company. If everyone's job title simply says assistant, you will have no idea who handles finance, who manages marketing, or who writes software. The same thing happens with AI. A poorly described tool creates confusion. The agent may choose the wrong tool, call it with incorrect inputs, or ignore it completely. On the other hand, a clear and detailed description helps model understand exactly. So what the tool is designed for, when it should be used, what kind of information it expects, what it will return. In many real-world applications, improving the tool description alone can significantly increase an agent's performance. So without changing a single line of code. In other words, good documentation isn't just helpful for developers, it's essential for AI as well. So the key takeaway, whatever we have discussed just now, so far in this session, we have explored how AI has evolved from single conversation system to intelligent agents, capable of completing the real-world tasks. The biggest difference can be summarized in one sentence: chatbots answer questions while AI agents achieve goals. Now, a chatbot is reactive. It waits for a prompt, generates a response, and then waits for the next instruction. So every interaction is largely independent. An AI agent, however, is proactive. Instead of responding to one prompt at a time, it can take high-level objective, break it into a multiple steps, decide what actions are needed, use external tools, and continue working until the objective is completed. So this represents a major shift from interacting with the AI through conversation to collaborating with AI that can actually perform meaningful work on our behalf. Next, the agentic anatomy. An AI agent isn't just large language model with access to its combination of several capabilities working together. First is reasoning, where the AI agent analyzes a problem, break it into a smaller task, and evaluates different approaches before deciding what to do. Next comes planning. Rather than thinking only about current steps, the agent creates a roadmap for achieving a final goal and can modify that plan as new information becomes available. So the third capability is tool use. AI agent extended beyond their training data by interacting with the APIs, searching the web, reading files, executing code, or communication with external applications. So these tools allow them to perform action, not just generate the text. So finally, there is adaptation. Agents continuously learn from the feedback and previous outcomes. If a strategy doesn't work, they adjust their approach, making them more reliable and effective over time. It's the combination of these four capabilities that transforms an AI model into autonomous agent. So as we look ahead, AI is moving beyond simple automation towards truly autonomous systems. The first trend is persistent operation. Instead of requiring constant supervision, future AI systems will be able to manage long-term tasks, monitor workflows, and work decisions with minimal human intervention. Second is becoming outcome focused. So rather than simply responding to prompts, these systems are designed to pursue objectives and continue working until those objectives are successfully achieved. So finally, we have continuous evaluation with external memory, retrieval systems like RAG, and feedback mechanism. So AI agents can improve over time by learning from more informative and past experiences. Together, these advancements represents the next phase of artificial intelligence systems that don't just assist us in conversation but actively collaborate with us to solve complex problems and achieve real-time outcomes. Now, next topic is memory. Now, the question arises, how AI agents remember information? So far, we have learned that AI agents can think, plan, and use tools. But here is something many people don't realize. That is, large language models don't actually remember past conversation forever. Every new chat is essentially a fresh chat. If you ask an AI about a conversation you had yesterday, it won't naturally remember it unless that information is stored somewhere else. It's gone. Imagine meeting someone every morning and who has forgotten everything from the previous day. For example, chatbot, that's not a huge issue. So for simple chatbot, that's not a huge issue. But for an AI agent that's expected to work for hours or even days, that becomes a serious limitation. Think about it. How can an AI manage a long project if it can't remember what is already completed? How can it personally respond if it forgets your preferences or learn from mistakes if every interaction starts from zero? That's why modern AI agents rely on external memory systems. Instead of strong memories inside the large language model, they store them in specialized database and retrieve them whenever they need it. So let's look at four main types of memory. Sensory memory. The first step is sensory memory. This is the information that agent is looking at right now. It could the latest user message, the output from a tool, or recent uploaded file. This memory exists only for the current moment. Once the next step begins, it quickly disappears. Think of it as quick glance rather than a long-term storage. Second is working memory. Next comes working memory. This is the agent's temporary workspace. It contains everything currently inside the model's context window. That include the ongoing conversation, recent tools outputs, the current objective, intermediate nodes, and reasoning. Unlike long-term storage, working memory has a limited capacity. So once the context window will fill up, older information begins to disappear. Third is episodic memory. Now let's move on to the long-term memory. Episodic memory stores experiences. Instead of facts, it remembers events. For example, last Tuesday, I helped this user build a sales dashboard, or the workflow failed because the API credentials were incorrect. So these past experiences are saved outside the language model and retrieved only when they are relevant. So it is similar to how humans remember specific events from their lives. Next is the semantic memory. The fourth type is semantic memory. Instead of remembering events, it remembers knowledge. Examples are like your preferred programming language, your writing style, comparing specific terminology, frequently used business rules. For example, the system might remember this user prefers concise explanation. They usually ask for Python code. They like step-by-step tutorial. So these facts are stored externally and loaded whenever they are useful. So the interesting part in both the episodic memory and the semantic memory are often powered by vector database. So we will explore those shortly. But before that, we need to understand another breakthrough technology that's changing how AI system access knowledge, and that is called RAG, Retrieval Augmented Memory. So RAG giving AI access to your knowledge. If you have been exploring modern AI, you have probably heard the term RAG. It stands for Retrieval Augmented Generation. Although the same sounds technical, the idea is surprisingly simple. So why do you need RAG? Language models have one major limitation. Their knowledge comes from the data they were trained on. That means they don't automatically know yesterday's news, your company's private documents, internal databases, confidence research, nearly created reports. So you also can't find hundreds of gigabytes of documents into a single prompt. So instead of trying to teach the AI everything in advance, we let it retrieve information only when it's needed. That's exactly what RAG does. Now, how RAG works? The entire process happens in 3 stages. Step 1, build the knowledge index. First, collect your data. This could include PDF documents, Word files, company manuals, databases, research papers. So these large documents are then divided into smaller pieces. So each piece is converted into a numerical representation called an embedding. So you can think of it an embedding as a mathematical fingerprint that captures the meaning of the text. Finally, all these embeddings are stored inside a vector database. Now the knowledge, is it ready to be searched? Step 2, retrieve the right information. When someone asks question, the process begins. First, the user question is also converted into embedding. The system then compares that embedding with the millions of stored embedding inside the vector database. So instead of searching for matching words, it searches for matching meaning. The most relevant piece of information are retrieved. So this becomes the context for all AI. Step 3, generate the answer. Finally, those retrieved documents are added to the prompt. The AI receives the user's question, the relevant context, instruction to the answers using that information. So instead of guessing the whole new response using your own data, the result is more accurate answers, up-to-date information, far fewer instruction hallucination, better business application. This is why RAG has become one of the most important techniques in modern AI systems. Now the importance of chunking. One of the biggest design decisions in a RAG system is something called chunking. Chunking simply means deciding how large each document segment should be. If the chunks are too small, important content gets lost. If they are too large, finding the most relevant information becomes difficult. So finding the right balance is essential for building an effective system. Next is hierarchical chunking. Engineers have developed an even smarter approach known as hierarchical chunking. Here is the idea. Small chunks are used during the search because they are highly precise. But once the correct section is found, the system retrieves a large parent section that provides additional context. So this approach combines the accuracy of a small chunks with understanding of a larger document. It's an elegant engineering solution. So agentic RAG, there is also an advanced version called agentic RAG. Instead of automatically performing retrieval at a fixed point, the AI agent decides for itself. It determines whether the retrieval is needed or not, which knowledge sources to search, how many retrieval rounds to perform, when enough information has been collected. So in this setup, retrieval becomes just another tool available to the agent. So that's specifically powerful for research assistants and complex business workflow. And finally, we have vector database, the memory behind engine. So now let's focus on one of the most important building blocks of modern AI system, the vector database. A vector database is specifically designed to store, organize, and search embeddings. So remember, embeddings are numerical representation of meaning. Instead of storing plain text, these database stores mathematical vectors. So why can't we use normal database? Traditional databases work well when you are searching for exact matches. For example, show me every customer whose name is John. That's straightforward. But AI asks a very different question. It wants to know which stored document are most similar in meaning to this question. Searching millions of vectors one by one would be far too slow. That is why specialist vector database exists. So searching millions of vectors efficiently. To make similarity search incredibly fast, vector database uses advanced indexing algorithms. So one of the most popular one is called HNSW, which stands for Hierarchical Navigate Small World. Instead of comparing every vector individually, HNSW creates a network of connection between similar vectors. So when a search begins, the algorithm intelligently navigates through the network until it reaches the closest machine. So the result dramatically faster search with only tiny reduction in accuracy. So for real world application, it's an excellent trade-off. Now measuring similarity with the cosine similarity. Once vectors are stored, the system needs a way to compare them. One of the most common method is cosine similarity. Rather than comparing the number directly, it measures the angle between two vectors. So if the angle is very small, the meaning they are closely related. If the angle is large, the meaning they are very, very different. Although the mathematics behind the scene, this technique powers most modern semantic search systems. So popular vector databases, several excellent vector databases are widely used today. Pincone is a fully managed cloud solution that is easy to deploy in production. V8 combines semantic search with traditional keyword search in one platform. Quadrant but uses Rust, focuses on high performance and advanced filtering. Chroma is a lightweight, beginner friendly and ideal for local development and experimentation. Milviews is designed for enterprise environment that needs to manage billions of vectors efficiently. And if you are already using PostgreSQL, PG Vector lets you add vector search directly into our existing database. So which one should you choose? So always there is a confusion. So if you are learning or building your first prototype, Chroma is one of the easiest option to start with. You can still set it locally within minutes. So for production application, many developers choose Pincone or Quadrant depending on their scalability and infrastructure requirement. Embeddings, turning meaning into mathematics. So we have mentioned embedding several times. So now let's understand what actually they are. An embedding is simply mathematical representation of meaning. Instead of storing word as a text, embedding model converts them into a long list of numbers called a vector. The fascinating part is that word with similar meaning produces vectors that are located close together in mathematical space. For example, the words puppy and dog would be positioned very, very close to each other. Cat would still be nearby but slightly farther away. Meanwhile, a complete unrelated word like car would appear in totally different region. So without anyone manually organizing the data, the model naturally learns these relationships during training. Semantic search, because meaning is represented mathematically, AI can search based on concept instead of exact word. Suppose a document contains the phrase automobile insurance. If someone searches for car insurance, a traditional keyword search might miss it. So semantic search understands that automobile and car represent the same idea and retrieve the correct document anyway. So that's what makes semantic search significantly more intelligent than traditional keyword matching. Embedding dimensions. Not every embedding model creates vector of the same size. Some model produces a few hundred numbers, others generate several thousand. So large vector captures more detailed relationships, although they require more storage and computational resources. So many open sources embedding models are efficient enough to run directly on a personal laptop, making experimentation much easier. So one rule you should never forget. There is only one simple rule that every AI developer should remember. Use the same embedding model for both indexing and searching. So if your documents are embedded using one model but user's query are embedded using another, the mathematical space won't match. So it's like comparing two complete different maps. Even though both contains useful information, they don't align. So as a result, retrieval quality drops dramatically. Keeping the embedding model consistent ensure your vector search remains accurate, reliable, and efficient. So to summarize, these four technologies work together to make AI agent more intelligent and capable. First, external memory allows AI agent to remember information beyond a single conversation, enabling long-term tasks and personalized interaction. Second, RAG or retrieval augmented generation gives AI access up-to-date and private knowledge by retrieving relevant information before generating a response. So the third is a vector database, store and organize information in a way that allow AI to perform fast semantic searches based on meaning rather than exact keywords. So finally, embedding converts text into numerical vectors, enables the AI to understand the relationship and similarities between concepts. Together, these technologies provide the foundation for AI agents that are smarter, more accurate, and better equipped to solve the real-world problems. Thank you everyone for watching this video. I will see you in the next video.